The entire discipline of supply chain management exists to solve a single problem: uncertainty. If customer demand, supplier lead times, and manufacturing outputs were perfectly predictable, you wouldn't need planners, you would just need a calendar. Yet, a common mistake in operations is attempting to manage this uncertainty by relying on a single, mathematically precise number. Planners often build their entire strategy around an average forecast. But if you stock inventory exactly to the average demand, you are mathematically guaranteeing a stockout half the time. By definition, actual demand will be higher than the average 50% of the time and lower the other 50%, trapping you in a continuous cycle of shortages and excess inventory. The average itself isn't the issue. The real threat is the variability, the noise and random fluctuations surrounding that average. When this daily noise is ignored or misinterpreted as a permanent trend, planners overreact, creating the amplified volatility known as the bullwhip effect. To actually manage a supply chain, we have to engineer the system to absorb forecast errors. That requires us to stop planning based on averages and start measuring the uncertainty itself. To turn unpredictable noise into calculable probabilities, operations rely on a specific mathematical model, the normal distribution, also known as the Gaussian distribution. This is a continuous probability distribution where data points naturally organize themselves in perfect symmetry around a central mean, creating a distinct bell shape. Under this model, the vast majority of outcomes cluster tightly near the center. As you move further away from that middle average, the probability of encountering an extreme value decreases smoothly and predictably. This clustering happens organically across operations. You see it in daily customer demand fluctuating around a baseline, in supplier lead times centering on a typical delivery window, and in the physical dimensions of manufactured parts varying slightly off a target spec during quality control. By applying this specific geometric shape to raw business data, planners can replace gut-level guesses with a rigid, probabilistic system. It allows us to calculate exactly how much safety stock is needed to hit a target service level. From a systems design perspective, the normal distribution is dictated by just two mathematical parameters. The first is the mean, represented by mu, anchoring the exact center. The second parameter is standard deviation, or sigma, defining the width and volatility of the dataset. This chart shows a perfectly normal distribution. The central vertical line at 0 marks the peak, where mean, median, and mode are equal. The entire yellow area equals 100% of possible outcomes, with tails extending infinitely without touching 0. Novice planners often focus entirely on finding the perfect mean. But the standard deviation is equally critical, because sigma is the exact measurement of the volatility the system actually has to absorb. The reason this mathematical concept aligns with messy reality comes down to the central limit theorem. The theorem states that when many independent random factors combine, like weather, traffic, and machine downtime affecting shipments, their cumulative effect naturally trends towards this exact normal distribution. We apply the empirical rule, this 68, 95, 99.7 rule, to map predictability. First, 68% of outcomes fall within one standard deviation from average. Expanding to 2 standard deviations captures 95%. Covering 3 standard deviations accounts for 99.7% of operations. This rule gives planners the ability to forecast the exact probability of an event happening. It completely removes the need to guess. We take this theoretical geometry and use it to calculate physical inventory requirements, specifically safety stock. Standard safety stock formulas assume demand and lead times follow a normal distribution. This structure allows planners to mathematically separate standard daily noise from true structural shifts in demand. To hit target service levels, planners cover demand up to a precise point, the green area. We calculate this using a z-score. Here, 90% fulfillment requires a z-score of 1.28. Notice the red area. Past it lies unmitigated risk, a 10% stockout probability. By using z-scores, supply chain professionals can translate abstract risk into financial reality. You can look at an executive and explicitly state that upgrading from a 90 to a 95% service level means paying to hold 2 full standard deviations of inventory. Now, in actual practice, real-world supply chain data rarely forms a perfectly symmetrical bell curve. This chart shows right-skewed data. Extreme outliers pull the mathematical average away from median reality. Notice how the mode, median, and mean lines separate here. Relying strictly on the average with a long, flat tail consistently underestimates extreme events, causing systemic understocking. Look at these intersecting curves. Certain operations encounter multimodal data or entirely different distribution models, such as the gamma distribution shown here, where the shapes behave very differently based on alpha and beta parameters. A common mistake is looking at asymmetric data and concluding the entire statistical framework is useless. But modern analytics tools don't assume normality blindly. They use the normal distribution as a structural baseline, testing the data for its best mathematical fit. The normal distribution is a necessary planning approximation. Starting with this baseline is infinitely safer than operating with no structure at all, allowing mature teams to continually adjust their models to fit reality rather than abandoning them. Mastering this specific distribution is what allows organizations to measure process capability, implement Six Sigma protocols, and actively prevent the bullwhip effect. Understanding this framework forces a shift in perspective. You stop operating as a scheduler reacting to daily emergencies and start acting as a system designer. This is why high-maturity organizations do not discuss single-number averages in their planning meetings. Instead, they discuss data ranges, they calculate exact probabilities, and build robust confidence intervals. True supply chain strategy requires replacing intuition with calculated probability. It is the only way to build an operation capable of absorbing the inevitable shocks of an uncertain world.